So these are amplifiers using transistors which are biased at a given current I0. Okay. We have already seen how to bias transistors at a given voltage and make amplifiers. That was the first thing we started off with. But then we argued, we reasoned out that biasing at a constant current will make the circuit less sensitive. So we will use that. Okay. We have 4 types of biasing, and including the replication of VGS, we have another technique to reproduce the current. So this is the first one, where we sense the current at the drain and feed it back to the gate. Okay. Here we sense at the drain and feed back to the source. Here we sense at the source and feed back to the source. And finally we have feedback to the gate while sensing the current from the source. So let's say we want to make a common source amplifier, right? Common source amplifier means that we should obtain an incremental picture like this. Okay. The signal must be applied between gate and source, and the output must be taken between drain and source, to which a load can be connected. So in the first case, it's quite easy to do that. With the first type of biasing, it's quite easy to do that. So what we want is the VGS here to appear across this transistor for DC, right? And we would like the small signal that we apply, which for now we can assume to be at above some frequency, above some lower cutoff frequency. Okay. Then we want that to appear across gate source at those frequencies. So how do we do that? If we have an input signal Vi here, how do we make sure that this bias appears across our transistor for DC and this signal appears across the transistor for AC? This is the DC bias. This is the AC incremental signal. We want essentially the sum of the two to appear at the gate of this transistor, okay, at this one. So this is the standard AC coupling technique that we have been using all the time. And we can connect the load to VDD, the power supply if we wish, and if we want to remove the DC bias at the output, we can use another capacitor to couple the signal. Okay. So the resistance and capacitance are large. I mean large meaning they are large compared to whatever things are connected in series, and also at the relevant frequencies. So you should be able to calculate the values of R large and C large given the frequencies of interest, okay, and the bias current I0. Now it doesn't pay to use the largest capacitor or the largest resistor because they tend to occupy more area and you will be wasting resources. Okay. So the large capacitance can be 1 picofarad also, depending on your frequencies of interest. So this is how we can make a common source amplifier, which is biased at a constant current I0. Okay, and we use the first biasing scheme. Is this okay? Now it turns out that the second one, this one is not very suitable to make common source amplifiers. Now the other day I mentioned that if you have very large inductors, you can always change any of these things, because if you connect inductors in series, the picture will remain the same for DC, but for AC everything will get isolated. After that you can connect things in any way you want, but they are not practical because you don't have large inductors. Now the reason this is not very suitable to making common source amplifiers is, you want to apply the input between gate and source and take the output between drain and source, but something else is connected to the drain. Okay, so it's not all that easy to do so. So we will not use this. How about the third one? Can we change this into a common source amplifier? So this is in fact the easiest one, and this is also probably the most familiar. You want the signal to appear across the gate source. Okay, so you incrementally, you ground the source for AC. You ground the source for frequencies of interest. Okay, and the drain doesn't have to be grounded or connected to the power supply. It can be connected to the power supply through a load resistor RL, and again you can couple the signal out like this. So the input signal is applied between this point and ground. Now this point is also AC ground because of the capacitor. Okay. Then this is probably the most common way of biasing the circuit, biasing the transistor at a constant current and making a common source amplifier out of it. How large should the capacitor be? If the lowest frequency is, let's say, F low, how will I decide on the size of the capacitor? What's that? I upon 2 pi FC. But what is that? That is not, that has some units, right? Very less compared to what? Which I not. Perhaps, yeah. But in terms of small signal parameters, so if I draw the incremental equivalent, the current source goes away and I have this capacitor, right? This is the load. If I apply certain VI here, what is the current that flows here? If the degeneration, if this capacitance is C, calculate it and let me know what is the current. You assume that it's an ideal transistor, meaning it has only GM, no GDS, etc. So it is of the form GM by 1 plus GM times the impedance that is connected between source and ground. Okay. And what do we want this to be equal to? GM. For a common source amplifier, we want this to be approximately GM. So the magnitude of GM by SC must be much smaller than 1. And we are interested in, the worst case is the lowest frequency. So, two pi times F flow times C must be much more than Gm. Okay. Is this okay? So, we can use two of these biasing arrangements to make a common source amplifier quite conveniently. The other two are not very convenient because you will have to isolate both the gate and source in this case or drain and source in this case. So, it is not very convenient, you do not have to use them. And in fact, this is the most common one. This is sort of the prototype common source amplifier that you see in textbooks. The only thing is in discrete design, frequently the current source is replaced by a resistance. Now, that works if the voltage, the DC voltage that appears here is very large. Okay. In that case, you can use a very large resistance and that will become equivalent to a current source with a very high impedance. Now, if you have a very small voltage, it is a difficult thing to do. Okay. Also, on ICs frequently, most of the time there is no reason to use resistors. In discrete design, you want to minimize the number of transistors you use because transistors are more expensive than resistors. Whereas in ICs, it is the opposite. Most likely, transistors will be less expensive because they occupy a smaller area. So, on an IC, you frequently use current sources. Most of the time, you use current sources. So, we could make common source amplifiers out of these two. What are the other things good for? Are they good for anything at all? Which circuit will be used to make a common gate amplifier? Can we use? Third one. Second one is? Yeah. So, if you look at the second one, this by itself is the biasing branch. Okay. Now, I replicate its current in another transistor. This is the circuit we had yesterday. It is the current mirror. It is a current mirror with higher accuracy and higher output resistance. Okay. So, can we make this into a common gate amplifier? Can this be turned into a common gate amplifier? How will you do that? So, there is nothing to do. You just apply the current signal here. If you think of a common gate amplifier as a current input circuit, the input current appears here, right? So, this transistor is the common gate amplifier. It already has a gate connected to a fixed bias voltage. So, this is also a very frequently used circuit. You have a cascode current source and this node I will call the cascoding node or cascode node. Okay. And you apply the input to that node. So, this is the common gate amplifier. Okay. And the load can be connected here. Doesn't have to be a resistive load. I have shown a resistive load here. So, this is how you do it. And if you have a voltage input, potentially you could connect a resistance and the input voltage to that point as well. Okay. Source of the bottom transistor. It is possible, like for instance, as I said, if you assume that there are inductors, then this is not grounded for AC and you can connect something here, but it's too inconvenient. Why did you want to do that? Okay. Yeah, you can do it, but it's not very convenient. Okay. Is this clear? We have a cascade current source. That is, we have a current source followed by a common gate amplifier. We use that common gate amplifier to improve the output resistance of the current source. Okay, but we can also use it to use it as a current buffer for current inputs. That's what is being done here. So this part is the biasing part, and here you apply the input signal. Okay. So can you turn anything else into a common gate amplifier? Where? Third one, yeah. So the third one looks like this, right? And you can apply a current input here. In fact, if you look at it, this part is exactly the same as this, isn't it? Which is okay. You can use, once you replicate the current, in this case, this part of it, the part that's enclosed in the box is exactly the same as the third circuit. So you can apply a current to the source and take the output at the drain. Then what about the last one? So if you look at the last circuit, it looks like this. Okay. Again, it turns out that you can apply a current. Okay. Now this does behave like a common gate amplifier. In fact, it's better than a common gate amplifier. You can go and analyze it. When I say better, its input impedance is even lower than that of the regular common gate amplifier. Why is that? So what is the input impedance of this? So let's say the gain of this is minus A. Okay. What is the input impedance of this? Let's have GM here, and then this is connected to a load. And for simplicity, I'll ignore GDS altogether. Okay. This is the gate, this is the source, and for the small signal incremental quantities, this is an open circuit. So if I apply a test voltage V test, okay, what is the voltage that appears here? Minus A times V test. So what is VGS? Minus A plus 1 times V test, which causes a current GM times this voltage in the upwards direction. Okay. So the current flowing out from the test port is GM times A plus 1 times V test, or the input resistance turns out to be 1 over A plus 1 smaller than that of a common gate amplifier. So it's an even better current buffer, and it can also be used as a common gate amplifier, or basically a current buffer. I shouldn't call it a common gate amplifier because the gate voltage is not fixed. But if you feed in some current I in, the same current flows here, okay, and the impedance looking in here is very small, and the impedance looking at the output is very large, okay. So that's how we can make current buffers or common gate amplifiers. The idea here is to make these amplifier stages which are biased at a constant current, so that the variation in GM with process and temperature is small, okay. And similarly, so if the variation in GM is small, the variation in small signal characteristics of the amplifier will also be small, smaller than if you bias it at a constant VGS. So what else is remaining? The common drain amplifier or the source follower. So which of these circuits can I use for the source follower? Which one can I use for the source follower? So if you look at this, in fact it looks like the source follower, right? Or common drain amplifier. The drain is grounded. Now the only question is where to apply the input, and clearly the input must be applied here, okay. The output is taken here. In fact, let me just call this some large signal input Vi and Vo, okay. So this is the source follower or the common drain amplifier. Again, a very common arrangement that you would have seen earlier. And in discrete cases with a large voltage across this, you can substitute a resistor for the current source, and it works more or less well. But on an IC, you almost always use a current source. So what is V0 in terms of Vi? We have already done the small signal analysis of the common drain amplifier. Let's just write the large signal equation. Can we do that? What is Vo in terms of Vi? It's just Vi minus the VGS of this transistor, which is Vi minus Vt minus square root 2 I naught by mu C ox W by L. Okay. Now, if you just look at this, if Vt is a constant, then everything else and mu C ox, all these things are constants. So simply, if you plot V0 versus Vi, this line corresponds to V0 equals Vi. Okay. So this characteristic is given by the straight line parallel to this. Okay. So what is the non-ideality that comes into picture here? Vt itself is a function of VSB, right? So Vt itself can be, if the bulk is connected to ground, Vt itself is dependent on V0. Okay. So what happens is Vt goes on increasing as V0 increases. So what does it mean? The separation between these two curves, this separation ideally was Vt plus the overdrive. Now Vt itself changes, so this does something like this. Okay. This separation now is the Vt plus overdrive, and Vt itself is increasing with V0. Okay. So it gives you first of all a slope that is not 1, right, and the output goes on reducing, reducing compared to the ideal source follower output. Is this okay? What I meant by that is, an ideal follower without any offset will simply follow this line passing through the origin. Now, if you did have the source connected to the bulk connected to the source, it would follow it with a fixed offset, and this offset is Vt plus square root 2 I naught by mu Cox W by L. Now, Vt itself is not a fixed quantity, so if we take some value of Vt here, that goes on increasing. So the actual output characteristics when the bulk is not connected to source looks like this. Okay. So this is the large signal characteristic of the source follower, pretty simple. And if you use a PMOS transistor, you can in fact make it follow this, except that how will you do it with a PMOS transistor? You will have a PMOS and a current flowing into the source. Okay. This is the input, this is the output. In this case, there will be a positive offset. V0 is Vi plus something. So it will follow a curve like this. Okay. Which other circuit can you use for the source follower or the common drain amplifier? Fourth one. How? Where will you apply the input, where will you take the output? Yeah, if it is an op-amp type thing, but it's not just the common drain amplifier, it's really the op-amp itself, right? Can you use the second one? Let's say I apply an input to the gate, okay, because I want to make a common drain amplifier, I know that the input has to be applied to the gate. So what will come out of the source? Is it similar to what we discussed so far? So what the large signal analysis we did so far applies exactly to this also, right? Here also V0 equals Vi minus Vt minus square root 2 I naught by mu Cox W by L. Now if you take Vi very high or take Vi very low, then the current source will be, this either this transistor will go into saturation, this will go into saturation if Vi is very high, and this will go into, this will go into triode region if Vi is very high, and this will go into triode region if Vi is very low. So if you respect those swing limits, you can still use this as a follower. Is there any difference between this and this. This is the traditional source follower or the common drain amplifier. And large signal wise, it looks like both of them give you the same output. Do they give you the same output? They do, I think. It's just Vi minus VGS, and it's the VGS at a current I0. At least for DC, there is no question that I0 is flowing through it. Okay. So what's the difference between these two? Is there any difference? Okay. So what does it do? That is fine. That's some detail, right? Because the way we bias, here we sense the current at the drain, here we sense it at the source. That's why the current source is on top, here it's at the bottom. Okay. And that is why here the drain is grounded, there it is not. That's fine. But besides that, as far as the characteristics of the common source amplifier is concerned, swing, okay. Even more basic characteristics. Even you have it here also, right? What is the input and output impedance in the two cases? Output impedance is the same. Input impedance is also the same, is it? Input impedance is not the same? No, output impedance is not the same. Okay. What is the output resistance in the upper circuit? Why? Anyway, you analyze it and see. Okay. You put GM and GDS for both the transistors and see what the output impedance turns out to be. Is infinite. So 1 over GM. Okay, so what happens? Okay, what he explained and also what he said earlier was that looking in here, it's infinite impedance because it's a common gate amplifier which is open circuited at the drain. That's the logic. Yeah. And looking in here, it's infinite impedance because it's a current source. Is that correct? Okay, yeah, GDS, fine. So, let's say the GDS was 0 for both transistors. You had only GM. Is the output resistance infinite? Huh? It can't be. Why? Or even if you assume a small GDS, it looks like the output impedance is large. Is that reasonable or no? Why? But how? What is wrong with this logic that looking up you see infinity because it's a common gate amplifier, open circuited? One second. And looking down it's also infinity because it's a current source. Okay, so what will be the impedance? It will be 1 over GM. So you can work it out. You assume the GM1, GDS1 for this, GM2, GDS2 for this, and please work out the small signal output resistance, see what it's going to be. Okay. Yeah, so roughly speaking, that's what happens. Yeah, so it is of the order of 1 by gm, it is not high, okay, but you can work out exactly and see what you end up with. Okay. What happens if GDS is 0? Still 1 by gm2? Huh? Not possible to find out. What do you mean you can't find out? You can certainly find out. Maybe the answer is not to your liking, but huh? No, you know everything. The circuit is right there. Anyway, you do it for this and you set GDS1 to 0 and see what happens. Okay. But anyway, it does behave like a voltage buffer, meaning it provides a low output impedance. So that's about what I had to say about the biasing circuits and how to use it in amplifiers. You can use in a practical circuit, you will have a number of these connected up in some combination. Okay. So what I suggest you do, if you're not very fluent with it, is you go and analyze each one of them and then try to manipulate it. And you can do the small signal analysis. If it's not immediately obvious to you what kind of amplifier it is, you do the small signal analysis, brute force, and that will give you the result, and that will also tell you what the gain is, what the input resistance is, what the output resistance is, and so on. Okay. So we now have, we know the basic amplifier structures, and we also know how to bias them in a way so that the amplifier parameters are relatively insensitive to process and temperature. We know that biasing at a constant VGS is not a good idea, right? At least biasing at a constant current seems to be a better idea. Whether it's the best, I don't know. Okay. So we started off with all this. We started the course by saying we want to make negative feedback amplifiers. So we can finally come to that. Okay. Before that, any questions on this? On the biasing arrangements as well as amplifier topologies using this type of bias?
So is there any way to fix the VT of the transistor even when you are not having access to the bulk of the transistor?
No. No. Because VT is determined by some process parameters, right? So I don't think you can fix it at all. When you have the control over the bulk, you can fix it, but that's because that affects essentially affects the inversion charge also. But otherwise, there is no method in circuit design will fix it. It's dependent only on how it's processed. Actually, we do have that. The question is, you talk about sensing at a particular node and feeding back to some other node. Can you feed back to two nodes? That's the question, right? So in a way, that is happening in this already, right? So essentially, what you want to feed back is VGS, which is VG minus VS. So you can either keep VG fixed and feed it back to the source. You can keep VS fixed and feed it back to the gate, or you can feed back a sort of differential signal to both gate and source. If you look at this, that's happening already in the fourth circuit. The feedback is applied to the source as well as to the gate. To the gate, it is applied through the amplifier. To the source, it's applied directly because of the implicit connection. When I started off analyzing those, or at least deriving those, I imagined a fictitious transistor like this, right? Where the controlling nodes are completely separate from the control nodes. Now this connection is already there in a real transistor. Okay, in the model of a real transistor, this terminal is already connected to this terminal. So that gives you implicit feedback. Okay. In fact, if you look at either this circuit or this, if you look at this circuit, there is no explicit feedback, right? You don't see any loop. That loop is inside the transistor itself. It's implicit in the transistor characteristics. So, because of that, in this case, there is feedback to the source as well as to the gate. So, that is possible. Anything else? We would like to implement feedback amplifiers, for which basically we need to implement a block diagram like this. Okay. In controlled systems terminology, it's G and H. Normally in circuits we use A and F or something. Okay. So this is an amplifier, and this could be, H could be an attenuator. So we know how to make an amplifier. We have all these different topologies. We have the common source amplifier, which gives you a large gain, and if you want more gain, you can possibly cascade more than one common source amplifier. Okay. So similarly, we know how to make attenuators. At least we know how to make resistive dividers. That's the simplest thing. How do you make this? You need to be able to subtract the feedback signal from the input signal. How will we go about doing it? But okay, one thing I have to, let me make this diagram more explicit and use circuit design terminology. For circuit design, let's assume voltage input, voltage output circuits for now. Okay, voltage is available with respect to a common reference. Okay, it's not available as a floating source. Floating meaning I don't have a source like this and I can take this and connect. I can take this whole thing and connect somewhere. Okay. Similarly, the input to this forward amplifier is with respect to ground, and it provides an output with respect to some common terminal, the same common terminal, and same with the feedback circuit. Okay. Let's assume that this is the case. Everything is referred to some common terminal. So then how will we do it? Is there any circuit you know which will take the difference between two voltages? I thought every circuit does that, right? You can use the gate and source terminal for sure, right? If I draw the picture of a common source amplifier, okay. So certainly it does take the difference between these two terminals. That is, the current flowing here and the output voltage are related to the difference between the gate and source voltage. Okay. So can we use it here to take the difference? What is the disadvantage of this? So I can apply, if I apply V1 with respect to ground here and V2 with respect to ground here, the current flowing in the common source amplifier will be related to V1 minus V2. Okay. It will be that times GM. Right. So this does behave like a block that takes the difference between V1 and V2. Okay. So can we use this for our feedback circuit? Why not? Oh, that's okay. Let's say, oh well, yeah, that is one thing, but let's say we can provide a bias. Maybe we can add a bias to one of them. So we will make it V1 plus V bias, where V bias is the required value for, some value that's more than the threshold voltage. What's that? Yeah, that's true. Again, that's going more into the detail. Just let's talk about taking the difference between two voltages, right? Does this circuit look the same from V1 and V2? What I mean is, I would like to, when I want to take the difference between two circuits, let's say I have V1, V2. Ideally, maybe one of the characteristics I am interested in is, here it is V1 minus V2. I don't care if it's voltage or some current related to this. Now, if I connect V2 and V1, I should get V2 minus V1. Now, you should also keep in mind that the sources that drive V1 and V2 don't have zero output resistance. They are not ideal voltage sources. Will that happen in our case? So that, when I say they are not ideal voltage sources, I am really hinting towards the input resistance, looking into this port and looking into this port. Okay. So is it the same? What is the input? So let's say I am interested only in V1. So I'll ground this. What is the input resistance looking in here? What is the input resistance looking in there? Infinite. Okay. So then I ground this and I look in here. What's the input resistance looking in there? 1 over Gm. So one of them is very large, the other one is quite small. Okay. So certainly it's not symmetrical. Actually, this circuit can be used. Before, in early days, this kind of circuit was used in feedback stuff. But it's not a great circuit because you can't use it universally. You have to know what you are connecting to the gate and what you are connecting to the source. Okay. Whereas, for instance, our op-amp model is such that you can take it to any circuit and use it. Because there, in an op-amp, you do know that the two inputs are symmetrical. Okay. So this has a very low input impedance looking into one of the inputs. Okay. So what do I do now? How will I fix the situation? I do have a block that takes the difference. Okay. So maybe I should write the complete common source amplifier. Common source amplifier does amplify the difference, but here it is high impedance and here it is low impedance. And ideally, I would like to have high impedance in both the cases so that whatever source resistance I drive it with, the voltage is not affected by the source resistance. Okay. So what do I do to drive a low impedance case? Actually, that is potentially possible, but what do you do? You will apply, if I apply V1, V2 here, you will apply V2, V1 here.
No, what I will sort the source and apply the input to the source.
Yeah, let's come to that. Actually. So what do you do if you have a low impedance load? If you have a low impedance load, what do you use to drive it? You will use a voltage buffer, right? You will use a buffer to drive it. So what I need is a buffer here. I don't drive it directly. I apply V1 here and I drive this to a buffer. That is possible, right? And what can I use for a buffer? Source follower. This is a source follower. Okay. And I do this. Will this work? Are the two inputs symmetrical now? At least as far as the input impedance is concerned, they are symmetrical, right? So I had a common source amplifier which amplifies the difference between gate and source, but looking into the source, I have a very low resistance. Okay, so whenever I have a low resistance load, I need a buffer to drive it, so that I drive a high impedance port and the buffer drives the low impedance portion. Okay, so that's what I have here. So I'll rearrange this so that it looks a little more familiar. What is this? So it's a differential pair. So we already know it, that's why we recognize it, but even if we didn't, perhaps by enough trial and error and reasoning, you would have come to this circuit. Okay. So now we have come up with a circuit which is symmetrical from both the inputs, right? And you can think of it as this transistor being driven at the source by this common drain amplifier. Okay. Now if you look at it, if you look below this line, the circuit is entirely symmetrical, right? So in fact, I can think of this as the common source amplifier which is driven by this one also. I can put the resistance here and make it fully symmetrical, and I can either say that I am driving the left one with the buffered version of the right one, or the right one with the buffered version of the left one. So this is one way of arriving at the the differential pair. Now we have to sit and analyze it, because the buffer we have doesn't have zero output resistance. Okay. So it's not like V2 will appear exactly here, isn't it? If you have zero output resistance, I started off by saying I drive this input with a buffer. If I have zero output resistance, then whatever the buffer's output voltage is without load will appear here with load also. But I already know that looking in here, I don't have zero output resistance. So it will be manipulated the voltage will be altered in some way. So I'll have to go and reanalyze the circuit. That I can do because I know circuit analysis. So the important thing is to come up with some topology that will do your job, right? After that, analysis is very simple. If you know Kirchhoff's current law and voltage law, you will be able to do the analysis. So we'll continue with that tomorrow. But this is sort of the workhorse of the feedback amplifier, right? So you have an amplifier with two inputs, and both inputs look symmetrical, and this is universal enough that it's used in every feedback amplifier that we know of, practically every feedback amplifier that we know of. Any questions?